right, let's do this example with Comet Hale Bopp. The comet Hale Bopp, one of the brightest comets seen in the last 40 years, has a perihelion of 0.914 AU and an aphelion of 370.8 AU. So its closest approach, it is just inside the orbital radius of the Earth, which would be 1 AU on average. And when it gets to its furthest point, it's 370.8 AU. This is a huge difference. And so as a result, it's going to have a pretty long period, a long time to make this trip. What is the speed of Hale Bopp at aphelion and perihelion? So I'm going to try and figure out what its fastest velocity and its slowest velocity. Because of its large orbit, the next time it will be seen is in the year 4,380. Well, maybe it will be seen in the year 4,380. That also means, on a second note, that the time before it was seen, when Mr. Foster saw Comet Hale Bopp, was last seen by the Egyptian pharaohs, was the last time that comet was seen. So let's go ahead and set this one up. So how we're going to do these comet problems is, I have two unknowns right now, so that means I'm going to need two equations. And the two equations we're going to use is we're going to use the conservation of angular momentum and the conservation of mechanical energy. And I'm going to explain why we can use those here. Okay, so we have I omega equals I prime omega prime. We can use this because if I think about I1 omega 1 plus I2 omega 2, the second object is the sun here, because there's no net external torques outside of the one between the sun and the comet. So we're going to ignore any forces from other planets on the comet. And then we're also going to actually end up, because the moment of inertia for that sun is so big, the omega for it is going to be pretty small, and there's not going to be a whole lot of change in that angular momentum for the sun. So we don't have to worry about much going on with the sun because it's so much bigger than the comet. So we're going to say that the I omega for the sun is about the same as it is afterwards. Okay, so we're going to cancel those two out and we're just going to be left with this. Now, whenever you have a point mass going around, we always remember that the angular momentum for a point mass is MeV and MeV prime. But let's work that out just real quick here. So I got mr squared for the moment of inertia for my point mass. Omega I can talk about as v divided by r. I see that those r's cancel and I'm left with my MeV there. And then we'll get the same kind of thing over here. So I get MeV prime. The mass will cancel. We are going to assume that the mass of our comet is staying pretty constant. We're also going to assume that there's no like outgassing or things like that really drastically affecting its orbital speed or anything. All right, so now we're down to just RV equals R prime V prime. So this has the two unknowns that we're looking for. We'll call this one maybe V and we'll call this one V prime. This R perihelion we'll just call R, and RA we'll call our R prime. Now we need to set up our work kinetic energy theorem. So as I go from point 1 to point 2, for our system, remember, we're still including the sun in there. And again, the sun is not going to change its position much because of this comet. So its kinetic energy, its potential energy, they do not change. And we also can then say, well, any work the comet does on the sun does back on the comet, so our work ins cancel in this multi-mass kinetic energy situation. So when I start out work in plus work done by friction equals K2 minus K1 plus UG2 minus UG1 plus there's no springs. When we do the suns, we say, well, the sun really doesn't change its kinetic energy. The sun doesn't really change its gravitational potential energy from going around some new point. And so the only thing that we're getting out of that is that this work in between the sun and the comet cancel out. There's no friction because there's nothing slowing down our comet as it goes around. And so now we're kind of left with this. Now point 1, I'm going to go ahead and call this point 1 here, this point 2 here. All right, so let's move the 1's over to one side. So I have 1/2 mv squared plus mgh, which in our case, ooh, not mgh, what am I doing? We got to use our gravitational potential energy at a distance, so negative big G, big M, little m over r equals, and then on this side we have the 1/2 mv prime squared plus negative big G, big M, little m over r prime. Now I have my two equations. What I do see here, which is kind of nice for me, is that the mass of the comet does cancel out. I do not need to know the mass of the comet. However, I do need to know the mass of the sun. Lucky for me, they do tell me the mass of the sun is 1.99 times 10 to the 30th kilograms. They also tell me AU, what that value is, because I will need these numbers in meters, not in AU when I plug it in. All right, so at this point, we are going to go ahead and solve for one of those two unknowns over here, substitute in. We'll go ahead and plug it in solver, see what we get. So let's go ahead and solve for V first. So I end up with V is equal to R prime V prime divided by R. Plug that value in over here. So now I have 1/2 times R prime V prime divided by R, quantity squared, minus big G, big M over R equals 1/2 V prime squared minus big G, big M over R prime. So a couple things I'm going to do when I type this into my solver is I'm going to put in these values not in AU, but in meters. The capital mass of the mass of the sun is 1.99. I knew that 1 AU, it told me, was 1.496 times 10 to the 11th meters. So go ahead and I'm going to multiply this by each of those, put that into my calculator, and hit solver. Now, when I do solver, I'm going to have to put a guess in. Okay, so we're finding V prime, so this should be a smaller number. The two solutions, well, there's only one solution, so it'll be negative or positive. So it's going to be a positive solution, so I'm just going to maybe guess like positive 10 or something like that. All right, so let's go over to the calculator quick. All right, here we have our equation. We're going to want to put that into solver. So we're going to head down to solver and clear out whatever we do have in there and type it in quick. I'm going to go ahead and wherever I see this V prime, which I'm solving for, I'm going to put in an X, and I'm going to label R prime as A and R as B, and then I'm going to use G and M as their values here. So let me type that in quick. All right, so now that I got my value typed in there, just go ahead and hit OK. Now I do have to put in the correct values here for these. So X is what I'm going to put in as my guess. This is going to be that slow speed. I'm going to put in a 10 guess there. Now these I do need to actually put in the correct values for those. So this was my R prime. So this is going to be my 370.8 AU. And I do need to multiply that by what an AU is. So let me just type that in quick. And then you can see I already have the G constant, the universal gravitational constant, and the mass of the sun already entered in there. So I just have to go back up and make sure that I'm hovered over the X when I hit solve, and I end up with 108.5. All right, let's head back to the board. All right, so from the calculator, we got that V prime value of 108.5 meters per second, which to you and me sounds very fast. But when you're talking about distances this far out, it's going remarkably slow out here, so that's why it's taking so long. The further out it goes, the slower it's going to go. Now that I know V prime, I can plug that number in. Again, here, does not matter if I keep it in AU in this equation. The reason I needed to switch it to meters over here was because I had this value here that was in meters, the big G value there. Once I plug it in over here, I find out the speed at the closest approach comes out to be 44,000-ish meters per second. It is moving significantly fast. So a very short portion of its life is spent near us where we can see it glowing from the sun, and a vast majority of time further out where it's not bright enough for it to illuminate thus that we could see it. So there you go. There's Hale Bopp.